today's video is on moment generating function of Poisson distribution. So this video is going to become a clear-cut video on mean and the variance of the Poisson distribution. See here, the moment generating function of a Poisson distribution is given as, if x is a Poisson distribution variable, then its moment generating function is given as e power lambda times of e power t minus 1. See, the proof of this one is, let x be a random variable having a Poisson distribution with the probability density function is given as, probability of x is equal to x is given as e power minus lambda lambda power x by x factorial, where x lies between 0, 1, 2, 3 and so on, and 0 otherwise. So this is the probability density function of a Poisson distribution. Now coming to the moment generating function of a Poisson distribution is given as mxt is equal to the expected value of e power tx. So this can be written as, so the moment generating function is equal to the expected value of e power tx can be written as sigma x is equal to 0 to infinity. So this is e power tx into probability of x comma some lambda, that is probability density function. So this is sigma x is equal to 0 to infinity. This is e power tx, and the probability of x is equal to x is nothing but e power minus lambda lambda power x by x factorial. This is e power minus lambda lambda power x by x factorial. See here, so e power minus lambda, so I am bringing it outside. This is sigma x is equal to 0 to infinity e power tx, and this is lambda power x by this is x factorial. Now this is power x and this is also lambda power x. See here, this is e power minus lambda, sigma x is equal to 0 to infinity. This is e power t, this is lambda whole power x by x factorial. Now see here, if I expand this one, this will be e power minus lambda sigma x is equal to 0 to infinity. So this is e power t into lambda by whole power x into x factorial. Now if I expand this one, so this is going to become e power minus lambda. See here, if I give x is equal to 0 here, anything to the power of 0 is 1 and 0 factorial is again 1. So this is 1 plus. If I keep x is equal to 1, this is e power t lambda by 1 factorial, and next one e power t lambda whole square by 2 factorial plus and so on. So this expansion is nothing but e power minus lambda into this is e power t into lambda. So now this can be written as e power. So if I take this lambda common, so from these two, if I take lambda common, this will be e power t, this is minus 1. So this is nothing but the moment generating function of a Poisson distribution is given as e power lambda times of e power t minus 1. See here, first of all, what is given here? Let x be a random variable of Poisson distribution with the probability density function is given as probability of p of x is equal to x is given as e power minus lambda lambda power x by x factorial. Now the moment generating function of the Poisson distribution is mx of t is equal to the expected value of e power tx. See here, this can be written as in terms of sigma, that is sigma x is equal to 0 to infinity e power tx. So here the function value, the e power tx into the probability of x comma lambda. So this is according to the probability density function of the Poisson distribution. This is e power minus lambda lambda power x by x factorial. Now see here, e power minus lambda is a constant term, I am keeping it outside. This is sigma x is equal to 0 to infinity e power tx lambda power x by x factorial. Now if I take this x common from these two, that is e power t lambda whole power x by x factorial. Now if I put x is equal to 0, 1, 2 and make a summation here, then this is the expansion of e power t into lambda. So now if I take this lambda common from these two, so this will be e power lambda times of e power t minus 1. So this is the moment generating function of a Poisson distribution. And now coming to the mean of the Poisson distribution, see here, mean of the Poisson distribution. So again, what is mean? The expected value or mu. So the expected value of p of x is equal to sigma x is equal to 0 to infinity x into the probability of x comma lambda, that is the Poisson distribution, the probability mass, the probability density function of the Poisson distribution. So this can be written as the mean value, the expected value is equal to sigma x is equal to 0 to infinity x into, according to the probability density function, we have this one, that is e power minus lambda, lambda power x by x factorial. So if I substitute this one, e power minus lambda, lambda power x by x factorial here, see here what happens. So this is going to become sigma x is equal to 0 to infinity, this is x. Now I am going to cancel this x. So for that I can write this as what is x factorial, that is 1 into 2 into 3 into 4 till x. So I am writing as x into x minus 1 factorial. Now I can easily cancel this x and see what happens. So this is e power minus lambda, which is a constant term. I'm bringing it outside. This is sigma x is equal to 0 to infinity lambda power x by x minus 1 factorial. Now see here, I have x minus 1 here and I'll make x minus 1 even on the numerator. So this is e power minus lambda. This is sigma x is equal to 1 to infinity. See what I'm going to do. This is x minus 1 and lambda power 1. So this is I'm multiplying with x lambda inverse into lambda power 1. So this is x minus 1 factorial. Now lambda is also a constant. I'm bringing it outside. That is lambda into e power minus lambda. This is a sigma x is equal to 1 to infinity lambda power x minus 1 by x minus 1 factorial. And see here, now I'm going to expand this one. So this is lambda into e power minus lambda. If I keep x is equal to 1 here, 1 minus 1 0, anything to the power of 0, and again 0 factorial is again 1. So anything to the power of 0 is 1. So this is 1 plus. If I keep x is equal to 2, this will be lambda by 1 factorial. And if I keep 3, then this will be lambda square by 2 factorial plus and so on. So what is this expansion? This expansion is nothing but e power plus lambda. Now e power minus lambda and plus lambda. If I cancel, so this value is lambda. Therefore, expected value or the mean of the Poisson distribution is given as lambda. So please note that mean. So the mean mu value of the Poisson distribution is lambda. And next coming to this one, that is variance of the Poisson distribution. See here, according to the variance of the Poisson distribution, we have a formula that sigma square of x is equal to e of x square minus e of x whole square. And see here, now I am going to calculate this expected value of x square. So this can be written as expected value of x into x minus 1 plus x. See here, I'm subtracting and adding x for my convenience. See here, first I am making expected value of x square and I'll substitute here. Expected value of x is nothing but the mean value, so mean square. So first I'm going to solve this. So this is nothing but e of x into x minus 1 plus the expected value of x. And see, so this is nothing but sigma x is equal to 0 to infinity. So this is x into x minus 1 into the probability density function, that is x comma lambda, plus the sigma x is equal to 0 to infinity. So this is nothing but x into the probability density function of the Poisson distribution, p of x comma lambda. So if I write so, that is sigma x is equal to 0 to infinity, this is x into x minus 1. So this is nothing but e power minus lambda, lambda power x by x factorial. And this is, see, sigma x is equal to 0 to infinity, this is x. So this is nothing but e power minus lambda, lambda power x by x factorial. Now I am going to cancel this x into x minus 1. So for that, the same thing, sigma x is equal to 0 to infinity. This is x into x minus 1. e power minus lambda, lambda power x by, so x factorial can be written as, I need x into x minus 1. The rest are x minus 2 factorial. And next one, see here, sigma x is equal to 0 to infinity. This is x. I'm going to cancel this x. So this is e power minus lambda, lambda power x. So this is x into x minus 1 factorial. Now I can easily cancel this x and x into x minus 1. And see what remains here. This is sigma x is equal to 0 to infinity. This is e power minus lambda, lambda power x by, this is x minus 2 factorial. And see here, this value is nothing but x is equal to 0 to infinity. This is e power minus lambda, lambda power x by, this is x minus 1 factorial. Now here in the denominator there is x minus 2 factorial. So I'll make x minus 2 even on the numerator. So this is sigma x is equal to 2 to infinity e power minus lambda. This is minus 2 and plus 2. See here, I am adding and subtracting. So this is x minus 2 factorial. And the next one, sigma x is equal to 0 to infinity e power minus lambda. So there is x minus 1 here. So I'll make x minus 1. So if I make x minus 1, so in order to balance, that is lambda power 1 divided by x minus 1 factorial. See here, now I'm going to split this one. So this is sigma x is equal to 0 to infinity e power minus lambda. This is lambda power x minus 2 into lambda square by x minus 2 factorial. And here also, see here, I made x minus 1. So I have to start with x is equal to 1 to infinity. So this is x is equal to 1 to infinity e power minus lambda, lambda power x minus 1 into lambda power 1 by x minus 1 factorial. Now I am sending this constants to outside, that is e power minus lambda, lambda square, that is sigma x is equal to 2 to infinity lambda power x minus 2 by, this is x minus 2 factorial. And here it is, see here, e power minus lambda, lambda power 1, this is sigma x is equal to 0 to infinity lambda power x minus 1 by x minus 1 factorial. Now if I expand this one, so this will be, see here, so this is going to become, so this value is nothing but e power minus lambda, lambda square. So if I keep x is equal to 2, 2 minus 2 is 0. Anything to the power of 0 is 1 and 0 factorial is again 1. And if I keep x is equal to 3, this will be lambda by 1 factorial. See here, and so on, lambda square by 2 factorial plus and so on. So here also e power minus lambda, lambda power 1. If I keep x is equal to 1, this is 1 plus lambda by 1 factorial plus lambda square by 2 factorial plus and so on and so on. So this can be written as e power minus lambda, lambda square into e power lambda plus, this is e power minus lambda, lambda power 1, and again this is the expansion of e power lambda. So if I cancel these two, then what remains? So here lambda square plus lambda. So what is this value? This is the expected value of x square. So after getting this expected value of x square, what is our variance of the Poisson distribution? The variance is sigma square x is nothing but e power x square minus e of x square minus e of x whole square. So e of x is nothing but the mean. So what is the mean value we got? So we got the mean value as lambda. See here, I'll show you the mean value here we got as lambda. See here, if you see, the mean we got as lambda, that is e of x is equal to lambda. So both the values we have, now I am going to substitute this one, that is a sigma square of x is equal to e of x square is nothing but lambda square plus lambda minus lambda square. So this is lambda whole square. So if I cancel this one, so I got the variance of the Poisson distribution as lambda. Therefore, the variance of the Poisson distribution is lambda. Here you have to note one thing, that the mean of the Poisson distribution, see here, This is the mean of the Poisson distribution. The mean is lambda and variance is also lambda. So here in the Poisson distribution, the mean is equal to variance is equal to lambda. See here, the lambda is the value here. So this is how we have to solve, and this is also so simple if you follow these steps. And in my next video I'm going to teach about the moment generating function of a normal distribution. Please don't miss it. If you really like this video, please pass it on to your friends, subscribe to this channel and support this channel. Thank you so much for watching.